In this segment, I want to talk about how to apply Newton's second law to uniform circular motion. So recall that uniform circular motion means an object moving in a circular fashion at a constant speed. Recall that that object is accelerating, that the acceleration points towards the center of the circle, and that we call it the centripetal acceleration. So we're going to be talking about how to solve force problems in circular motion. So in a way, it's nothing new. In a way, it's just applying what we've already learned in Chapter 5 to a new situation. But it is different enough. There's enough differences that I feel like it deserves its own section, and there's a whole section in the book devoted to it as well. So here's a list of steps. And it's going to build heavily on our list of steps that we had just for regular force problems. So if you may need to review that real quick if you're not feeling confident on that in order to move on to this section. In order to solve circular motion force problems, we do the same thing that we do for straight line force problems. It's just that now, there's just a few little tweaks we need to make. So for horizontal motion, we're going to set up our coordinates so that we are looking edge on at the circle. And so for horizontal motion, what I mean is an object moving like this, right? So this is what I would call a horizontal circle, right? The plane of the circle that the object is moving in is horizontal. So we would want to set up our coordinate system looking edge on like that, okay? For vertical motion, so this would be vertical motion. This is a vertical circle. You're going to want to set up your coordinates so that you are looking at the circle face on. In other words, like this. So this is sort of a complicated way of saying just always do a horizontal view of the motion. Now, you of course could have some motion that was like kind of diagonal, neither horizontal nor vertical. I'm not going to ask you about that. There's no reason why you couldn't do a problem like that. It just gets a little more complicated. I just won't ask you about it. So we're going to constrain ourselves to either vertical circles or horizontal circles, okay? And either way, you would want to set up your coordinate system from this perspective. Recall that the times when we want to use an alternative coordinate system and not just our standard xy is when the acceleration would be through two dimensions or something, right? And so the book suggests, and I think it's a great suggestion, I completely agree, that we always make positive towards the center of the circle. There are some sign errors that you're just going to avoid if you just follow that rule, right? Why? Because we know that the centripetal acceleration always points towards the center of the circle. And so by making positive x towards the center of the circle, then you will always have the right sign on your centripetal acceleration if you follow these rules, right? So we're going to make positive x towards the center of the circle in either case. And the acceleration in the x direction will be the centripetal acceleration. And so we will have the situation where the sum of the forces in the x direction equals ma sub c. I will always make it so that the acceleration in the y direction, as defined here, will be 0. Okay, so that's our basic strategy. It's just a force problem, but we have to be a little bit careful with our coordinate system. That's all. So I think we should take a minute and consider the centripetal force. Now, I've not actually used that term in these lectures yet. I have used the term centripetal acceleration. And you know what? I'm not going to use that term centripetal force again after this, really. Why? Because just as a centripetal acceleration is not like a new kind of acceleration. I mean, it's an acceleration that points towards the center of the circle, and but it's still meters per second squared. It's not like different from the acceleration we learned about in Chapter 2. It's just sort of a different application of it, right? And so too, the centripetal force is not a new kind of a force, right? And the book does not use the term centripetal force either. The reason is because there's been research showing that if you use that term centripetal force, then students tend to think that it's another force that goes in our catalog. You know, the misconception tends to be, oh, we've got normal force, weight, friction, drag, centripetal force. Oh, no, that's not the case. That's not the case, right? We have normal force, weight, friction, drag, any of those can provide a centripetal force. So I think it's important when you're dealing with a circular motion force problem that you take a minute and pause and consider what is providing the centripetal force. The sun went behind a cloud. I'm going to take a moment and adjust my lighting scheme so we don't have quite such a gothic vibe going on in this lecture. So, the moon orbits the Earth, right? Is the moon moving in circular motion? Absolutely. Then, is it accelerating? Yes, it is. It has a centripetal acceleration. Well, then there must be a force that's causing it to accelerate. The moon is orbiting the Earth. The moon is orbiting the Earth. What force causes it to stay in circular motion? Well, it's gravity, right? So there's not gravity and a centripetal force. Gravity is providing the centripetal force. Maybe I've got, maybe you're driving around a corner in your car. Okay, so you're driving around a corner in your car. Are you moving in a circle? Yes, you are. Then are you accelerating? Yes, you are. It's a centripetal acceleration which points towards the center of the circle. What's providing the force that makes it so that you can turn? Well, imagine trying to do that on a very slippery, icy road. You wouldn't be able to do it. So what's providing the force? It is friction. There isn't a centripetal force and friction. Friction is providing the centripetal force. Okay, so it's important to recognize what the force is that's causing the circular motion. Remember, accelerations are speeding up, slowing down, or turning. And remember that it's a force that causes acceleration, which means a force is required to turn a corner, a force is required to speed up, and a force is required to slow down. So, when you're thinking about these circular motion force problems, we want to be thinking, what is providing the centripetal force? It could be a combination of forces, but usually I'm going to ask you problems where it's just one force. Okay, let's dive in and let's solve a couple of problems. And I think you'll see what I mean when I say, well, it's just a force problem. We're just going to do those steps we've done for force problem. Okay, let's do it. A typical highway curve has a radius of 150 meters. What is the maximum speed that you could take this corner without slipping if mu sub s is 0.4? So again, we've got this car going around a corner. What is providing the force that causes it to go around a corner? Well, it's friction. And again, imagine it going, trying to do this on a very slippery ice rink. It would not be able to do it, right? So it is friction that's providing the force that's causing the centripetal acceleration. So this is a force problem. Let's just dive in. First, we should draw a picture. Here's my car. Lovely car. And, well, we should back up just a tiny bit. Is this a vertical circle or a horizontal circle? Well, unless this is like a stunt car, it's not. It's on a highway. This is a horizontal circle, okay? So we're going to do a edge on view. That means we're looking like this, okay? So always we're looking horizontally. So here's the back of my car, and let's say that it's doing this, into the board. So it's moving into the board at this point, and the center of my circle is over here, which means that R is right there. That's a lovely picture. Next, we should do a free body diagram and define our coordinates. Well, let's see. We've got a normal force up. We've got the weight down. And we have the friction force right here. Is it static or kinetic? Well, unless he's peeling out, it's static friction, right? So as long as there's no slippage between his tires and the road, then it is static friction. And notice they did give us mu sub s in this problem. Okay, so static friction, weight, normal force, that's all of the forces. Now in our list of steps it says, make towards the center of the circle positive x. So let's do that. In this case, it ends up being a standard coordinate system. But be careful, I picked this not just because it's standard. I picked it consciously, and it's well thought out, positive x towards the center of the circle. Again, our motivation is to make the acceleration in the x direction. That's our motivation here. Okay, what's our next step for a free body, or for a force problem? Next, we should sum the forces in the x and the y direction. Now, in this case, I told you in the previous slide that the sum of the forces in the x direction is going to be MAC. And I know that's true because I've set up my coordinate system in that way. Now the car is not going up or down, so we also have the sum of the forces in the y direction equals 0. Okay, well, what forces do we have in the x direction? Well, I only see one. Remember, Newton's second law is a recipe. It says take all the forces in the x direction and add them up. Okay, let's follow the instructions. All the forces in the x direction, there's only one. So this is just F sub s equals ma. Now it says the fastest, right? So let's not forget that Fs max equals mu sub s times the normal force. Can we use this? Are we at the maximum? We are, absolutely. We are at the maximum. Why? Because we're looking for the maximum speed. Therefore, we want the maximum static friction force, right? If we were to drive a little bit slower, the static friction force would be less. That's all right. We'd be able to go faster if we wanted to. Okay, so we're going to plug that in here for Fs. Okay, well, notice that A, what about A? I think we should plug in for A. We know that the centripetal acceleration is v squared over r, right? Okay, so now looking at this, we've got r, we're looking for v, m. Don't give us m. We don't know n. Oh gosh. Maybe we're on the wrong track. Wait, we haven't finished all of the steps for our force problem yet, have we? Because we haven't applied Newton's second law in the y direction. I'm really sure this is a force problem. Let's just keep going with our steps and hopefully it'll work out. Okay, let's see what happens. So we're going to do the sum of the forces in the y direction. Ooh, we've got a positive normal force and a negative weight. So we've got n minus w equals 0. That tells me that n equals w. And of course, w is m times g. So now what we can do is we can take this normal force and plug it in right here. And notice what happens. My m's cancel. And we can simply solve for v. So we end up with v equals the square root of mu sub s times g times r. And that equals 0.4 times 9.8 times r. What did they tell us r was? 150 meters. And now, when I run my calculator, I get, and we'll just, I'm out of room down here, so we'll write my answer up here. V equals 24 meters per second. Okay, let's interpret that. 24 meters per second, something like 50 miles an hour. The very fastest you could take a highway curve without slipping, if mu sub s was 0.4, it's a reasonable number. Yeah. They better have some warning signs if that's the case, right? Okay. Pretty good number. Again, this is the maximum speed that we could take this corner without slipping. Another note here, this will happen a lot, right? Your masses cancel. If you think about it, there's a lot of situations where the magnitude of the force is proportional to the mass. And of course, the mass is the inertia, right? And so there's a lot of situations where the mass cancels. For example, if I just drop a ball, right? If I drop a big, let's say I drop a big rock and a little rock, right? If I've got a big rock and it's 10 times heavier than the little rock, well, they both fall at the same rate, right? That's because gravity is pulling 10 times harder on the big rock, but the big rock is also 10 times harder to move. In other words, the force is proportional to the mass, but its inertia is also proportional to the mass. And so those two things cancel. We're going to see that a lot, right? And in this case, Its inertia is proportional to the mass. How hard it is to move is proportional to the mass. And the force that's causing it to move is also proportional to the mass. And so again, they cancel. Okay. I'm going to erase the board, and then we'll do another example. Okay, here's another example. A handful of professional skaters have taken a skateboard through an inverted loop in a full pipe. For a typical pipe with a diameter of 14 feet, what is the minimum speed the skater must have at the very top of the loop? Okay, well, this is a force problem. It's hard to tell that, isn't it, right? Because it's looking for minimum speed. Ooh, but, you know, a lot of times if we see this language, minimum speed, maximum speed, especially if we're dealing with a circular situation, it's a pretty good key that it is a force problem. But don't be afraid if you're not sure to just try something. Like maybe you treat this as maybe you think it's a projectile motion problem. I don't know. I'm going to guess you just won't get very far. You'll start on it and you'll be like, this isn't working. Hey, just try something else. Oh, maybe I think it's a 1D motion problem. You wouldn't get very far on that either. Try a force problem? Let's see how far we can get with that. Okay, so first let's draw a picture. A full pipe, so that would be like this. Typical pipe with a diameter of 14 feet. So that means we've got a radius of 7 feet. What's a foot? Let's convert that. How about 2.13 meters? Okay, so we've got a radius of 2.13 meters. We've drawn our picture. We're going to treat it like a force problem. We've drawn our picture here. Well, is this a horizontal circle or a vertical circle? Well, it's a vertical circle. So we should draw our free body diagram edge on. But let's see. For a typical pipe, what is the minimum speed the skater must have at the very top of the loop? Presumably that means in order to not fall off, right? So if our skater's at the top of the loop, there he is, okay? Then what's our object of interest? Well, the skater. Let's draw our free body diagram. What do we have? Well, we've got certainly the weight down. Always the weight down. What else? Anything else? How about a normal force? Isn't he on a surface? Normal force is always perpendicular to the surface. In this case, that would be down, I guess. It must be. Yeah, there we go. You know, when you've got a situation like this where you got forces overlapping each other in the same direction, you know, drawing them on top of each other just makes it confusing. Although, I guess you could. So I'll just draw them kind of right next to each other. But let's just recognize that this is, you know, a vector is not a bendy arrow. These are right next to each other. They're overlapping, really. But drawing them that way isn't very helpful. There's my free body diagram. Great. In our list of steps, it says make positive x towards the center of the circle. What? Where's the center of the circle? That's down there. So that means that I'm going to do that with x going in that direction. Can I do that? Sure. Why not? X is positive towards the center of the circle. That is in this direction. Again, why? Because we're drawing our free body diagram for the skater at the top. That's our moment in time that we are analyzing. Okay, free body diagram. Got that business. Next, sum of the forces in the x direction. Let's see what happens. Well, we've got W and N. Are they positive or negative? Yeah, they're both positive, aren't they? Because I've called down positive. There it is again, M. I didn't give you the M in the problem. Should we give up and go home? Oh, wait, I'm already at home. That won't accomplish anything. No, we should not. We should have faith in the process and hope it cancels. Yeah, this is a tricky part. This next step, I'm going to go ahead and put it into the category of a trick. The first time you might be like, what? Second time you see it, you'll be like, yeah, that trick. Third time you see it, you'll be like, oh, it's that thing again. Fourth time you see it, you just be like, know that. Okay, here's the trick. What's the minimum speed the skater must have at the top of the loop? In order to what? In order to not fall off, right? Mathematically, how can we say he fell off? Well, he's no longer in contact with the track if n equals 0 when the skater falls off. Okay, so what we're going to do then, we're going to let n go to 0. And notice what that does. Weight is, of course, mg. That equals mv squared over r. My masses cancel. Oh, goody. And we have v equals the square root of g times r. 9.8 times 2.13. And now we run our calculator and we get 4.6 meters per second. Okay, 10 miles an hour, fairly reasonable, fairly reasonable. I don't know. I've actually never done this, so I guess it's reasonable. Math certainly works out. I can imagine a skater going 10 miles an hour. Okay. You know, a lot of times when I throw this problem out the first time, students will say, oh, well, the minimum speed is just 0, right? It's just 0. But imagine that he was stopped when he finally made it to the top. Ooh, just barely stopped. Wouldn't he have fallen off way back over here, right? He's got to have some speed in order to make it around, right? Kind of like you could fill a bucket with water and you could go like this. You could swing it around your head just fine and no water would come out. But as you went slower and slower, you'd be in more and more danger of getting a wet head. And it's not when it stopped up here, right? If it stopped up here, you're already wet, right? You got to keep it moving through that top in order to not get that water to dump on you. So v equals 0 is definitely not right. V equals 4.6 meters per second. I like it. Okay, you know, again, the thing to really notice here is that it is just a force problem. It's just another force problem. So, in a way, this could go in Chapter 5. Okay. Last topic that I just want to mention real quick, that is going back to this idea of centripetal force. And I'm going to, again, like I mentioned, I'm not going to really use that term very often after this lecture. But there's another term that you really won't hear me use at all, and that's the centrifugal force. And so I just want to take a moment and talk about these two forces. So again, the centripetal force is whatever force causes you to move in a circle. So let's imagine that you are in your car and you're driving pretty fast and you go around a corner. Okay, so I'm driving my car, I'm going around a corner like this. Okay, what is my experience? I'm here, and I feel, the car's turning like this, right? I feel like somebody's pulling me to the side, right? I feel like I'm getting pulled to the outside of the car. Is there something pulling me to the outside of the car? There's not, right? Remember Newton's first law. Newton's first law says, an object in motion will continue to move in a straight line at a constant speed unless acted upon by a net force. So, you are sitting in your car, and your inertia wants you to just go in a straight line, right? Newton's first law says you're just going to go in a straight line unless something pushes on you and causes you to not go in a straight line. So you're going in a straight line. Meanwhile, your car, which has a lot of friction acting on it from the road, is doing this. So your car does this, and you try and go in a straight line. Well, what happens? You feel like you're being pulled to the outside of the car, but really it's your car that's being pulled in that direction, and your inertia is carrying you in a straight line. There's really nothing pulling you to the outside of the car. But that's what the human experience is like. It feels like that, right? So let's give it a name. Let's call it the centrifugal force. But it's not a real force. It's not a real force, right? It's only felt by observers in a rotating reference frame, right? In other words, if I'm standing on the side of the street and I'm watching you go by, I'm going to be like, there's no force on that person pushing them in this direction. There's just not, right? There's no agent, right? If you're the object, there's no agent pushing you in that direction. No, but you in the car, you feel it, right? So it's only noticed by somebody in a rotating reference frame, which is physics we're not going to get into in this class. And so it never goes on a free body diagram. It's an apparent force. You also see it called a pseudo force. It's not a real force because it doesn't cause accelerations, right? Okay, so that's it. I'm never going to talk about the centrifugal force again. Centripetal force is a real force, but it's what causes centripetal acceleration, but it's not a new force. It's just a way of classifying all of the forces that we've already learned about. As I've said before, a normal force, weight, friction, or tension, they can all act as centripetal forces. Again, I probably won't use that term very much either. I will use the term centripetal acceleration because if something is undergoing uniform circular motion, then the net force is causing a centripetal acceleration.